Hello students. In today's class we are going to be introduced to the concept of drift velocity and resistivity. So to start with this class, today's discussion, for us it is very much important to revise what we have read so far so that we can see the continuation as well as we can understand from where this concept is been arising and how it is important. So if we are revising, in the previous class we were introduced to a term known as resistance, which is provided by the electrical equipment known as resistor. Other than that, one law we have studied which deals with resistance is Ohm's law. Okay, so we have segregated our material into three classes, and these three classes are based on the resistance they provide. Like the first one is conductors, second one is semiconductors, and third one is insulator. So here it depends upon the resistance they are providing. We have seen that the conductors provide the minimum resistance. Now to what? Resistance is provided to the motion of electrons in the material. Motion of electrons or charged particle in a material under consideration, and this material can be an electrolyte, can be a solid, okay, as we have seen it can be a solution, okay. This material can be a solution, a solid, or an electrolyte. Now, conductors provide minimum resistance to these electrons or charged particles, whereas semiconductors have their separate properties. They work under the condition of doping and non-doping. When they are doped, they behave like conductors, and when they are pure, they behave like insulators, and we can say the conductivity in the pure state of semiconductor is extremely less. Extremely less. Now the insulators are extremely resistant towards the flow of electrons or charged particle. So they provide maximum resistance. Okay, now we will study all these cases in a particular material. I have considered this material. There are these electrons. Okay, now the case one is we haven't provided the electric field. Sorry, it should be 0. We haven't provided the electric field E equals to 0. Okay, so now these electrons will go through a random motion. Every electron will have its own velocity, and overall momentum of the system, if we consider momentum of the system is 0. When momentum of the system is 0, mv equals to 0, v is supposed to be 0, but we are saying that these electrons are possessing their own velocity. So we will introduce a concept of average velocity, and this average velocity do exist. Now see over here, these electrons are moving in this particular path. This electron is moving in this path. They are following what kind of path? It is a zigzag path. Okay, they are not following a normal equalized path, but they are following a zigzag path. Okay, so I'll just rub this space to utilize it. We'll see it like our electrons. When they are moving randomly, following up a zigzag path. So overall momentum, if we consider, sometime it is higher, sometime it is lesser. So average momentum, we have taken it as 0. Whereas the average speed we have taken as v. And this thing, now if we consider, we have introduced these electrodes, or we have introduced a second case where E is not equal to 0. We have provided electric field. Now in this case, what happens? These electrons starts drifting towards the opposite electrode. So this drifting, how these electrons are drifting, generally gives us an idea of resistivity. In insulator, if we see, when we provided the electric field, this drifting is extremely low or slow. Drift velocity extremely less. Okay, so the motion of electrons seen in this case is null. So they provide high resistivity to the motion of, or to the drift of, the charged particle or electrons. Okay, but when the case comes of the conductors, once we have provided the electric field, then what happens? There is quite a good drift velocity. We will see zigzag motion. We will see average momentum to be 0, and some velocity which we termed as the drift velocity of our charged particle or electrons. So from this concept comes the concept of drift velocity and resistivity. Now let's see what exactly drift velocity is and how can we derive a expression which can define for us the drift velocity in a given piece of conductor or a conducting body. Drift of electrons and the origin of resistivity. Electrons suffer collision, emerges out with same speed after collision, but random direction. Now just think, you are moving and you met a friend after some 10 kilometers of walk. You are going around 15 kilometers away from your home to get some good quantity of something you wish to have. Okay, so you have walked up to 10 kilometers and you met your friend for like, after meeting your friend, you were talking with him for 10 minutes and you forget what you want to buy. Now you reversed your direction and you reached back to your home. What is it happening? It is like you are colliding with your friend and reversing your direction back to your home instead of doing your work. Same happens with these electrons which are present in the conductor. They aim at traveling in this direction. Once they collide with the another electron, they deviate from their path. It is not exactly the 180-degree deviation, the way I have said, like you return back to your home, but it can be any kind of random direction. This electron, once interacting with this electron, can go at 45 degrees from the original direction, or can go 180 degrees from the original direction, or can go 270 degrees from the original direction. So this is what called random direction. We cannot predict at what angle this electron gonna get deviated. Okay, now to derive one particular formula to explain the drift of electrons, we will consider all the electrons is having a average velocity 0, since they have random direction. So we have averaged, given the average for this particular group. There are many electrons and these all electrons have random velocity. But when we summed up all these velocity, we have given V average is 0. V average is 0. Now if we consider that there are capital N number of electrons and the velocity of the ith electron in these, like we have n number of electron, and in this we have considered the ith electron. This electron is having a velocity at a given time. It can be given as vi, then 1 upon n, that is number, we are giving average, right? Average is number of, like v1 plus v2 plus v3 dash 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 up to Vn divided by number of velocities we are considering, n number of velocities. So n number of electrons we are considering over here. Sigma of all the velocities of all the electron from I equals to 1 to I equals to capital N, which gives us 0. This is averaging velocity. We are here averaging the velocity. Now next to it is when we have applied the electric field. Electric field is present, then all the electrons will be accelerated. Just see, like these electrons are randomly showing a motion in this conductor. Now if I apply an electric field in this direction, this negative electrode will repel our electrons, whereas the positive electrode will attract our electrons. Okay, so in this case we will see acceleration of these electrons. Acceleration, its dam will see a acceleration. Now just think, like you are there and you are asked to go to market, but you are not in a mood. Now your mother said that you can buy your favorite milkshake from the market. What will you do? You will run to the market to get the item along with your milkshake. So same is happening with the electrons. Electrons are very lazily moving, showing the lazy behavior and moving inside the conductor. Now we have applied an electric field, we have given them the motivation. Now they will show the acceleration. So that acceleration is given as A equals to minus EE upon M. E is the charge, capital E is electric field, and M is the mass of the electron or the charged particle under consideration. Again considering the ith electron having Vi velocity after last collision at time Ti, then its velocity Vi at T is given by this motion of equation. This is motion of equation. What is this? Final velocity equals to initial velocity plus acceleration into time. This is the first motion or first equation of motion. So over here Ti is the time under consideration and this minus EE upon M is acceleration. See equation number 3. And Vi is initial velocity and capital Vi is final velocity. Capital Vi equals to final velocity after time T. Now average velocity is sum of all the capital VI's, that is final velocities. Final average velocity equals to Vi upon capital Vi upon N. Because just after collision, that this will give final velocities for just after collision, it will give random direction, hence Vi sum is again 0. Capital Vi is also 0. Initial Vi is also 0. Why so? Because they are following the random motion. Now collision of the electrons do not occur at regular interval but at random times. In our conductor, the motion of electron, collision of electron, drift of electron, everything is random. There is no systematic way that this electron will move for these many meters and then deviate. No, it is exactly like a random, and like by their heart they want to do, they are doing that. Nobody is forcing them, nobody is asking them to do that, and no one has given them the time like at this particular hour you have to do this or something like that. Okay, so it is basically about them being random in the atom or in the conductor. They show the random motion, they have no average velocities, as well as their final momenta is also 0. So these collisions are also not systematic but are random. Okay, let us denote tau as the average time between the successive collision. Now we have given one new term, that is the tau, and it is the average time between the succession. It can be 1 minute, it can be 1 second, it can be 0.1 second or 0.11 minute or anything, because collisions are random. Now, then at a given time, some of the electrons would have spent time more than tau and some less than tau. It's simple. Time can be more than or time can be less than. So why is it so? Because electrons are showing random collision. Random interval for collision. Okay. Now average value of Ti is tau. This we have taken as tau as the average time. See, we have taken tau as average time. So when we are saying that this is the average time, this gives us T1, T2, T3 and so on. Okay. This average value of Ti is tau, also known as relaxation time. Also known as relaxation time. In this time, in this interval, these electrons are bit relaxed over their motion. Now averaging the equation number 3 over the n number of electrons, equation number 3 over the n number of electron given time t gives us for the average velocity Vd. This is average velocity, that is our drift velocity. So this is given as Vd equals to Vi average. This is capital V. So this is the after collision velocity after collision. Velocity after collision. It is equals to small Vi average minus Ee upon a m Ti average. This is acceleration. This is the time. Again, this comes from the first equation of motion. Then this initial averaging is 0. So our this will become as 0. Okay, this whole thing will become as 0. Why? Because initial average speed is 0. We have taken 0 minus E upon m tau. So it will give us this value. So I will write over here Vd equals to minus E upon m into tau. That is the drift velocity. Its sign is negative. We got the results where electrons move with average velocity which is independent of the time, although the electrons are accelerative. This is very much important as it says it's independent of the time. This phenomena is known as drift and the velocity Vd is called the drift velocity. Because of the drift, there will be net transfer of charges across any area perpendicular to E. Like this is the direction of E. There will be electrons moving in this direction. Consider the planar area A located inside the conductor such that the normal to the area is parallel to E. Now we have considered this particular area. See, E is going here. This is the whole area which is parallel to E. E here over here, and this is the area. Okay, this is cylindrical planar area, cylinder which is having a planar area A. Okay, see over here, this is del x which is equals to drift velocity into a change in the time. Here is the electric field applied and these are the electrons trying to move from this direction to this direction, opposite the direction of E. Opposite the direction of E. Now, then because of the drift in an infinitesimal small amount of time, del t, all electrons to the left of the area at distances up to this would be crossing the area. Now, why this del x equals to Vd into del t is taken as? If we see, because see, what exactly happens is drift velocity into time. Distance is always given as speed into time. So here speed considered to be drift and time is t. That's why the equation came del x equals to Vd into del t. Now if we are considering n is the number of free electron per unit volume in the metal, then there will be n del t Vda such electrons. If we say this is the electron, this is the volume, volume can be given as our area into number of electrons into this particular distance. For n electron, this A and del X will make the volume. What is volume basically? Volume is a three-dimensional concept. For this cylinder, we have to find the volume, that will be area into its thickness. And from the previous equation, we know the thickness can be given by del x. So area into del x, thickness or length, okay, anything is fine. If we see cylinder, this is our cylinder. Over here, this is the area and this is considered to be x. Del x is its length. So area into length will give us volume and number of electrons are n. Now we have to change del x, so it will be A into V dt into n. So this comes our equation. This is for number of electrons in a given volume. Now we will see over here is the other point. Since each electron carries a charge minus E, the total charge transported across this area A to the right in time del t is minus n into E. From where this E is coming? This E is coming from the charge. Now we are talking about the total charge transported. Now we are talking about the total charge transported. Hence we multiplied this equation with E. This equation with E. This equation is charge, number of electrons into volume. Here and volume equals to area into length. Okay, and our length is equals to velocity into time. This is what I am explaining over here. I'll give one like point to point derivation at the end of the video. Also, this is for the explanation. Into the whole equation as such, now E is directed towards the left and hence the total charge transported along E across the area is negative of this. E is directed towards the left. We have seen in the previous diagram of the cylinder, E goes from here to, from this point, this right side point to the left side point. And the charge, what is the motion of charge? In the opposite direction, already told. See, it's very much universal that our charge E will move against capital E, that is electric field. So if electric field is moving towards the left, charge will move towards the right. Now the amount of charge crossing the area A in time del t by definition is I del t, where I is the magnitude of the current. If we see how much charge normally is crossing, it is I into t, time, current into the time. We know that current equals to charge per unit area, charge per unit time, sorry. So charge will be current into time. This is what? So this is our general equation and this is our from drift velocity. Now we are equating the equation from this point and equation from this point. See, I del t equals to plus NEA Vd del t. Now del t and del t will get cancelled out and we will get the value of I as NEA Vd. See over here, this is what we are going to get. Substituting the value of Vd now. Vd equals to minus E square A upon EA upon M. So this minus and already there exists a minus will get cancelled out. We will get this particular equation. Then from here we will introduce the um, magnitude of our current density. I have provided a video where I have explained what is current density before this lecture itself. So to revise the current density, go and watch that also. Now I equals to J into A, current density into area, where current density is denoted by NE square M tau of E, and the vector representation is given by J bar equals to NE square M tau E to the vector, power to the vector. Okay. Now sigma equals to NE square upon M tau. Here sigma is the resistivity. So sigma is given as NE square upon M into tau. Here assumption is that tau and N are constant and independent of electric field. Okay, so these are the derivations. Now it's time for us to revise all of it to understand, and then we will derive it once again, without the statements. The previous one was with the statement for your better understanding. Now it's for us to know what we have derived so far and how it is important for us to understand all these things. Okay. So see over here, first thing is that when we have applied the electric field, we will be giving some voltage and it will be proportional to the length. Like see, this is our conductor where we have given electric field in this direction and motion of electron is in this direction. This is the length del x as we have seen previously. So this is the first relation which we have seen in the previous lecture where we have read about the Ohm's law. Now the force can be defined as E into E. This is the force. It's a product of charge into electric field, and then the force can be written normally as Fm. Okay. In general, we have read that force equals to mass into acceleration. Okay. So from this we have taken mass into acceleration equals to E into E. Now from this equation we will see that acceleration's value is coming minus E upon M. This is how we have defined the value for acceleration or the formula of acceleration of electrons in our case. Acceleration of electrons in this case. Okay. Now we will see that there are free electrons and we have considered that n number of electrons are present. Number of electrons. So I will denote here U as the initial velocity and V as the final velocity. So for n number of electrons, U average can be written as 1 upon n into U1 plus U2 plus U3 and so on up to our UN. Now this will become, U average will become 0. Now similarly, I will go for the final velocity. This final velocity V equals to U1 plus acceleration into tau 1, that is our relaxation time for one electron. Similarly, for the second electron it will be given as U2 plus A tau 2. Similarly, if we keep on going for Vn, it will be given as Un plus A tau n. Now we will try to find the average in this case. For that we have Vd, that is our drift velocity. Vd equals to drift velocity. Okay. Now Vd equals to V1 plus V2 plus V3. It goes up to Vn and the whole divided by capital N, number of our electron. Now we will substitute the value of V1, V2, V3. Okay. Vd equals to U1 plus A tau 1. Similarly, U2 plus A tau 2. Similarly, it will go up to Un plus A tau n and the whole divided by 1 upon n. Now we will get equation for Vd as U1 plus U2 dash 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 upon Un and another equation as A tau 1. This is in addition. Okay, always remember A tau 1 plus A tau 2 plus A tau 3 up to A tau n, and this is divided by the capital N because capital N is number of our electrons. This will also be divided by capital N. Now changing it up, we will get Vd equals to U plus A tau. That is general equation. So now we'll go with finding out the relation between drift velocity and resistivity and current. First of all, let's see about J. What is J? It's current density and given by current upon area. Current density and given as current upon area, where I is current, A is its area. Now we have this can be given, current is NE A VD upon the whole area, which will give us the value of NEVD. A and A will cancel. That is the value of J. This is the value of J. Now, next to it, we know that conductivity is given as sigma equals to Ne square tau upon M. Okay. How come this is coming? We have substituted the value of Vd in this equation. Our Vd is Ne into E upon M. This is our Vd. So it will give us a value of Ne square E upon M. From this equation we have found out the equation for the conductivity. What exactly the conductivity is? E equals to, like, sigma equals to J upon E. So we have substituted this to get our value of this. Now this resistivity of material, this is what conductivity. From this conductivity we can find resistivity. Resistivity is denoted by rho and it is given as M upon Ne square tau. This is a star marked equation. One should know. This is resistivity. Now we know that our drift velocity equals to ev tau upon ml. From where this VL is coming? we have got it from the E. We have seen E equals to V upon L. From here we are getting this equation. Okay? Now V is the potential difference. Capital V is the potential difference across the ends of the conductor. E is charge, tau is relaxation time, L is the length. And from here we can find the voltage. From this equation we can find the V, potential difference. How come? It will be V equals to Vd ml upon E tau. That is our potential difference across the conductor of length capital L. And from here again we can find the another new formula for the Vd, that is ml upon area into n into E square tau, the whole thing multiplied by I. Now from where it is coming? It is coming, we have substituted the value of Vd. What we have did? We substituted the value of Vd. Okay. Now this is our conclusion equation for the voltage or the potential difference across the conductor. So what we have seen here is the relation between drift velocity and resistivity. Additionally, in this lecture we have found the potential difference across the length of conductor and sigma, that is conductivity. Okay, so this is a extremely important relation. So that's all for today's class. In the upcoming class, we will read about mobility. Mobility is another concept which is same as the drift velocity, but I have given a separate lecture on the mobility so that we'll have a better understanding what's mobility, why it's important, what's its role play in the conduction and resistance. So that's all for today's class. We'll see we'll meet up in the next lecture where we'll talk about mobility. Have a good day, guys.